10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
Hi everyone, I am Madam Rosmaya. So today we are going to continue with the topic electric field part 2. So we have discussed in the previous video electric field part 1 about the region for a point charge, positive charge. So the electric field pattern is radially outward, whereas for the negative point charge, the electric field pattern is radially inward. And also we have discussed the formula E equals to F per Q. So this is definition of the electric field. Right? And for the for further derivation from this equation, we derive electric field equals to Q per 4 pi epsilon naught R squared. So R is the distance from the charge. Yeah? Okay, so now we continue with the question that we discussed before. In the electric field part 1, we have discussed the electric field at position P here. But today we are going to discuss the electric field when at the position in the middle between A and B. Okay, charge A and charge B. Okay, so now let's start. We know that for the point charge, positive charge, the pattern of electric field is radially outward. Okay, like this. So at point P, the direction of the electric field should be in the to the right. Yeah. So just choose one line from the electric field. So along the line joining A and B, so the electric field is to the right, okay, to the right or towards B. Okay, we do the same for point charge B. For point charge negative B, the direction of the electric field is radially inward. So we just choose the line of the electric field that lies along the line joining AB. Okay, along AB. So that's mean this one. Okay, so we bring it here because we want to determine the direction of electric field at P. So the whatever charge that we put here will experience the electric field by these two charges. Okay, by these two charges, charge A and charge B. Okay, so using the formula E, where the resultant of electric field here will be EA plus EB. Okay, EA plus EB. Why? Because they are in the same direction. And from here, we can see that the resultant electric field direction is towards B. Okay, look at the arrow here. Okay, now to calculate the E, we use the formula that we derived in the electric field part 1. We have discussed before. So E equals to Q per 4 pi epsilon naught R squared. Okay, we need to find distance first. Okay, so the given that the diagram, okay, from P, this is a right angle, okay, 90 degrees. So 10 centimeter, 10 centimeter. So we can use Pythagoras theorem to find the distance AB. So R equals to square root of 10 squared plus 10 squared. Okay. So solve this, we get 14.14 centimeter. Yeah? Okay, so now we can substitute everything into the equation. So for EA, electric field comes from charge A, so that's mean 2 microcoulomb times 1 per 4 pi epsilon naught is 8.99 times 10 to the power of 9 divided by r squared. So distance will be half of 14.14 centimeter, so divided by 2, and then 14.14 convert to meter, so bracket squared. Next, for the EB, we do the same. So 8.99 times 10 to the power of 9 times 8 times 10 to the power of negative 6 microcoulomb. Okay, we convert to coulomb. And then distance also 14.14 times 10 to the power of negative 2. Okay, convert to meter per 2, half of the distance. P is in the middle, AB. Okay, so the answer is 18 times 10 to the power of 6 Newton, and towards B, because the question asks find the magnitude and the direction of the electric field. Okay, so done for this example. Okay, next we are going to discuss about motion of a charge in a uniform electric field. So the uniform electric field example is in the between the two plates here, the two plates. Okay, just now point charge. Now the plates, one is positively charged, another one is negatively charged. Okay, two charged parallel plates. Okay, the direction of the electric field is from positive to negative, and you draw it equal in distance because they are constant, or uniform. So let's say E, electric field, and then if we put a charge, okay, positive Q here, and what happened, okay, the charge here will attract to the positive plate, while for the negative plate, okay, the charge here will experience a repulsive force, okay, repulsive force, and here attraction force. So what happened, this charge will move towards the negative plate. Okay, so let's say the force is F, electric field E, and the charge is Q, coulomb. So from the F equals to QE, okay, this one we, from the definition of the electric field, okay, electric field is F per Q, so cross multiply, the force is QE. Okay, from the F equals to MA, okay, so you substitute this into here, we can calculate the acceleration of this charge. Okay, so A equals to QE per M. Okay, this is acceleration of this charge. Okay, this is another point of view. If it is negative charge, start from the negative plate. So negative and negative repel, repulsion force involved here, so that's why it moves towards the positive plate. Okay, the acceleration can be calculated using the same method just now. Okay, so how we get the electric field just now, how we get the electric field just now, direction of electric field pattern just now for the plate. One is positively charged plate, another one is negatively charged plate. Okay, refer to the positive plate, direction of the electric field, remember from positive, and from positive, okay, so to the left, okay, to the left, and another one to the right. So same goes as negative plate. So for negative plate, the direction of electric field is towards the plate, so showed by the green arrow here. Okay, green arrow. Okay, from the right side also. Okay, now what is the resultant? Okay, the green arrow and the red arrow shows the direction of electric field individually, okay, by each plate. Okay, so the resultant will be, okay, on the left side, what happened? The resultant of the electric field will be 0. So that is why there is no electric field, okay, on this side. Same things happen here. Okay, so the electric field in this region is equals to 0 because the resultant is 0. One is to the right and another one is to the left. You see the direction, green arrow and the red arrow. Okay, but what happened in between? Okay, in between they are same direction. Okay, you see green arrow this way and the what you call this red arrow is this way. You see this arrow because out of the positive plate. So you see this part this part. Okay, so the resultant is to the right. Okay, the resultant is to the right. So that's why when we draw the region, okay, to represent electric field, okay, it will become like this. So on the right side and on the left side, okay, on the right side, the electric field will be 0. Okay, here 0. So only in the middle, electric field has value magnitude in the middle, and the direction is from the positive plate to the negative plate. Okay, like we discussed in the previous slide. Okay, if we put the charge from here and the charge is moving downward, so what happened to the charge? Okay, arrow shows here the charge move downward. So this positive charge will attract to the positive plate. Okay, positive charge attract to the positive plate because it's unlike charge. Okay, so let's say the velocity is v. So this charge experience the force because it's a positive and negative charge, unlike charge, repulsion force given by this F. Okay, and it is equals to QE, QE. And what happened? The charge will follow the projectile, okay, path. Okay, it's a projectile actually. Okay, the trajectory is a projectile. Okay, and the shape of the path is parabolic. But after it come out from this area, so it will continue follow the straight line. This one is a straight line, no longer parabolic. Parabolic only from within the plate area. Okay, from here to here. After the plate, okay, it will go a straight line path because of the inertia of the charge. Okay, so straight path, and the direction is tangent to the curve of the parabolic here and when it ends here. Okay, so this is another animation shows how the charge this is positive charge because this is positive, so it attract to the negative plate.